So recall in an analysis of variance, what you're going to have to be able to do are these bulleted points. So you start out with basically all but the last one are going to be covered in your ANOVA F test. You define the parameters, what are the different population means you're comparing, state your hypotheses, give your decision rule, either calculate or write down the calculated value of your F score. A lot of times we're going to just assume the method is valid, but really the idea is you have independent samples collected from each of your different factor levels or groups, populations that you're comparing. What is your p-value? Then you make your decision about whether you reject the null hypothesis or fail to reject the null hypothesis, and then state your conclusion. Either there is or is not evidence that there are differences among at least two of the population means, or not all the means are the same. The next thing is coming up with a way to look at each pair of comparisons or each pair of populations and compare two at a time to locate which means are significantly different than other ones. So we're going to use technology to actually do something called Tukey multiple comparisons. So again, let's go back to our example where we have a tire manufacturer trying to decide which of four tread designs is going to be best on a new tire. So they put tires on cars, went to 45 miles per hour, and then tried to stop as quickly as they could, and they measured how long it took to stop for 15 observations for each of four tread designs. So what are the steps you would take after finding a significant difference from the ANOVA F test? Well, there are two methods that are often used to determine which population means seem to be different. The procedures are called multiple comparison methods. A lot of times they'll be called post hoc analyses. But the idea is you can either use confidence intervals or hypothesis test to do this. Now we're going to use a method called Tukey. Tukey was a statistician about a century ago who came up with methodologies based on looking at differences of sample means and behaviors of those things. This is a example of how you compare what's called the family-wise error rate, and we'll talk about what that means as we go through different examples. But the idea is you're going to be making more than one statement. You're going to be analyzing more than one confidence interval. So you want to be able to say for the multiple comparisons for all the values, all the statements I'm making, I'm 95% confident that simultaneously they all are correct. And that's sort of what the Tukey methodology and some of the other methods that are out there attempt to do. So what we're going to have is we're going to have output, and I've sort of honed this down a little bit. So what you're going to focus on is the Tukey 95% or whatever level is given, simultaneous confidence intervals, and it's going to be given such as, one thing subtracted from, and then you're going to have a table. So when it says A subtracted from B, that means mu sub B minus mu sub A could be anywhere from the lower limit, which is about 0.2, to the upper limit of about 9.3 or 9.29. And then you'll do the same thing. So what we're going to do is we're going to create a table to analyze all the 6 comparisons and draw conclusions. Now, if 0 is in the interval, we're going to say there's not a significant difference in the population means. But if 0 is not in the interval, then we're going to identify which mean is larger and which mean is smaller in this. So what I do is I'm going to write down what my comparison is. So mu sub B minus mu sub A. Keep in mind it says A subtracted from, and then it gives you B, C, and D in that first table. So what that means is A is the second thing in the calculation or in the subtraction. So it's mu B minus mu A. You've got to get the order correct to get the right interpretation or right conclusion out. And then for mu B minus mu A, notice the lower limit was 0.20, the upper limit about 9.29. Both are positive, so when you subtract and you get positive numbers, that means the first value, mu sub b, is going to be more than the second value, mu sub a. So that would be our conclusion. Now if you go to the second line in that first table, it's, a subtracted from c, so mu sub c minus mu sub a goes from 0.13 to 9.22. So again, both are positive, so that tells me the first value, the mean for tread design C, is more than the mean for tread design A. Now look at the next one. Mu sub D minus mu sub A. Now we get a lower limit that is negative, negative 6.41, and an upper limit that is positive, 2.68. So since it goes from a negative to a positive number, 0 would be included in the interval. So what this is going to tell me is that I can't really make a determination. I can't say that the two means are significantly different. So I would write no significant difference there. The next line is mu sub c minus mu sub b. So I'm just going to page back and show you now we're in the second table where it says b subtracted from c and b subtracted from d. And then the last line in the table on the next slide will be the c subtracted from d. So mu c minus mu sub b goes from negative 4.62 to positive 4.47. Again, negative to positive, so that tells me zeros in the interval, they could be the same, so I'm going to write no significant difference. The next line is mu sub d minus mu sub b, and now I've got two negative numbers, negative 11.16 to negative 2.07. Both are negative. So now what that tells me is that the second value, mu sub b, is larger than the first value, mu sub d. So I'm going to say the mean stopping distance for tread design B is more than the mean stopping distance for tread design D. And then the last line, mu sub d minus mu sub c, has negative to negative, negative 11.09 to negative 2. So again, I can conclude the second mean, mu sub c, is larger than the first mean, mu sub d. Now look at your conclusions. Look at all 6 of those statements. And what can you say? Well, you know that A and D have lower values, lower means, lower stopping distances than either B or C, but you can't tell the difference between A and D, and you can't tell the difference between B and C. But if you were trying to give the best stopping distance, you want it to be smallest, and can you at least cut down from having 4 different tread designs? And you can if you think about what all those statements mean. So with 95% confidence, I can conclude the mean stopping distance from 45 miles per hour for all tires is lowest for either tread design A or tread design D, but I can't really distinguish between those two designs. But I know that A and D are better than B and C. Tread designs B and C both have larger mean stopping distances than tread designs A and D, so I know I can eliminate B and C. So what I would do is further testing for designs A and D in this case. So this is the type of analysis you would do after the ANOVA F test. If you get a small p-value, you reject the null and say yes, somewhere the means are not all equal. So the first thing I would ask you to do is the F test, right, to see if there's any usefulness in looking more deeply at the information. So if the test is significant, so you conclude there are differences among the population means somewhere, then you would complete the table of pairwise comparisons, or the Tukey multiple comparisons, using the confidence interval approach. Now the output will probably give you differences and give you p-values. Really what you want to do is focus on the confidence intervals and make sure you can read those. If you had a p-value less than some given significance level, it's going to tell you the same type of directional information as a confidence interval, but the confidence interval is going to tell you how much the two population means are different. So the confidence interval actually gives you a little bit more information. Now you don't have to do a formal validity check, as I mentioned, for ANOVA questions, but just realize that you should be able to know what they are, or if you see them on the formula sheet or whatever for a test, you should be able to apply them if asked to do so.